In today's lecture, we will be looking at the ensemble methods, specifically the boosted aggregation and the boosting, which are called bagging and boosting algorithms. So far, we have seen training individual hypothesis functions or classifiers. Now, it is a matter of human experience that instead of having one person judge, if you have a committee of people sitting and judging, so they tend to give better decisions. So, the same idea is extended to classifiers, where instead of having to train one classifier for a particular problem or one hypothesis function for a particular problem, you train multiple of them. So, why do you do this? Remember that in our discussion on the bias and variance, so variance term had this particular hypothesis which we called as the aggregated hypothesis or the average hypothesis. So, variance mathematically is nothing but the deviation of the aggregated hypothesis from the hypothesis that we have trained on a particular data set, correct. It was h bar minus hd in our notations, okay, distance between them. Now, if you want to reduce the variance, we will have to ensure that whatever we train on one particular data set is close to the aggregated hypothesis h bar. So, how do we do that? One of the ways to do it is to train multiple hypothesis functions, okay, on multiple data sets and take an aggregation. So, now this shows that it is guaranteed theoretically that if you take classifiers that are trained on multiple data sets and average them, your error will be lesser compared to training an individual classifier. So, that is why ensemble methods are extremely powerful in the sense that you can always find an ensemble that is having a better performance compared to individual classifiers, and most of the commercially available classifiers that are used in industries are ensembles because of this particular reason. And we will also see that the individual classifiers that are being ensembled need not be very good, in the sense that they can be weak learners. It is called weak learner. Every individual component of an ensemble is called a weak learner, in the sense that they just have to be better than chance. Suppose you are solving a binary classification problem, random decisions will give you 50% accuracy. So, any classifier that gives you less than 50% accuracy in a binary classification problem is a bad classifier, right, because it is worse than chance. So, I keep seeing this. I give them a 10 class classification problem. So, they come and tell me that they have built a classifier that gives them 5% accuracy. Well, random chance will give you 10% accuracy, right. So, everything that, I mean, a weak learner has to be better than chance. So, whenever you create ensembles, the prerequisite is all the individual hypotheses that we learn have to be weak learners, in the sense that they are better than chance. As long as they are better than chance, ensembles always are guaranteed to give you better accuracy compared to individual classifiers, because of the fact that the variance is the difference between the aggregate and the individual classifier. Now, the problem, the practical problem here is that we will not have. So, remember what h bar was. So, during the discussion on Bayes variance decomposition, h bar was the expected classifier, where this expectation was on a distribution over data sets, okay. But we only have one data set in practice, so we do not have multiple data sets. So, what do we do is the question. If we have multiple data sets, of course, we can train multiple classifiers and average them. Since we are given only one single data sets in practice, how do we ensure that we compute this expectation is the question. Now, what is the closest thing that you can do to this expectation is approximate this expectation by creating data sets by doing a sampling with replacement, okay. So, in ensemble methods, expectation over PD is approximated via creating data sets by sampling with replacement. Create multiple data sets by sampling with replacement and then build hypotheses and then average them. So, that is what ensemble methods will do. So, we will look at multiple ways to do ensembling. One of them is what is called as boosting. Which is simply sample with replacement to create ensemble. Now, if we do this, then suppose so data set D contain ensamples create B training sets by sampling so that each new data set DB d small b has ensamples. Okay. If we have capital B number of data sets, each of which have exact same samples or ensamples. So, we know that there is a okay, let us simply do the math maybe. So, now since we are uniformly drawing, right. So, probability of a sample xi being picked is 1 over n, probability of xi not okay with xi not being a part of a data set dB. How do we calculate this? 1 minus 1 over n. 1 minus 1 over n is the probability that a sample is not picked in one draw. If you do n draws, you will have to multiply this n times, right. So, now if
so dB has n samples less than n samples.
No, exactly n samples, you are doing sampling with replacement.
No, if the whole data set itself has n examples,
yeah,
then again creating a subset of n examples doesn't make a sense, right? If I have n examples, again creating one more subset, it's just replication of the same thing. Unless the order matters.
Why? There can be duplicates, no? When you are doing sampling with replacement, there will be duplicates. Of course, there will be duplicates. Yeah. So, that is why the probability of a particular sample not being a part of an entire data set is 1 minus 1 over n raised to n. So, at limit, so if you take n to be going to infinity, then this is a standard limit, right. What is this equal to? 1 by e, which is 0.36, okay, which means that this 36% chance, or rather roughly 36% of the samples will never be a part of the data sets that we use to train classifiers. So, this has an implicit regularization effect, because it creates an implicit validation data in the sense that this is coming for free. When you ensemble, there are samples that are never seen by any of the individual classifiers, right. So, when that's one of the reasons why. Now, we will show how to exploit this in a while, okay. So, the aggregation train B independent classifiers or trees So, call them f1 of x. Okay, we have been using h for classifiers, right? We will use h2 of x, so on up to hb of x. So, the final prediction is simply y cap for the bagged case is simply the average. Okay. So, if it is classification, we will approximate this by taking the majority out if you have n of them. If it is regression, you just take a numerical average of it, that is it. Okay. Now, one question that is to be answered is, when we are, can we do any better, in the sense that when we are sampling, there are two questions here. How do we sample? Right now we just sampled with replacement and we gave equal importance to all of the samples. The other thing is, how did we train the individual classifiers? We just trained them doing an ERM over whatever sample data sets that we have. Can we do something else? Can we do something better here is the question. So, there are algorithms that will improve both of these things. Okay. Adaboost, for example, does not do a sampling with uniform weights, it will do a sampling with specific weights that are learned, we will see that. Gradient boosted trees will not train every classifier on the entire data set, but it trains it on a subset of data set, as we will see now, and why that is of importance is a question. We will answer all this in a while. Okay. Now, let us look at the idea of random forest. Yeah.
Each sample which we take from data is given to each classifier, 1 to 100.
What is the question?
If we have B classifiers, to B samples, each of the sample of the data set is given to one of the classifiers. What reason?
So, you train one hypothesis on one data set, right? You, by sampling you get one data set, train it on, train one classifier on one hypothesis on this. Okay. So, let us look at, this is bagging. Oh yeah, sorry, this is bagging. See, boosting is a special case of bagging, as we will see. Yeah, thanks for noticing that. Okay. So, now let us look at the variance of the ensemble. Let's look at how to calculate this. Now, we train B individual classifiers, right? So, for suppose Zi represent a random variable corresponding to the prediction of a hypothesis, of the ith hypothesis on a given data point. See, since a hypothesis function is a deterministic function and we have stochasticity on x, the prediction also has a stochasticity, right. So, let Zi represent a random variable that is simply the output of the ith hypothesis for a given data point. Okay. Now, so how many z's we will have now? B of them, because we have B hypothesis functions. Okay. Now, since all the hypotheses are trained on the same set of data, or other, or data coming from the same distribution. Data sampled from a given distribution we assume Z1 through ZB to be identically distributed. See, please note that I am not saying that they are statistically independent. Actually, that is the catch. They will not be statistically independent. Why is that? Because we have data points that are repeating by construction, but we can assume that they are identically distributed. Okay. Now, therefore, let the variance of the individual classifiers, all individual classifiers, be represented by sigma squared for all I. Okay. They are not statistically independent, since we are doing sampling with replacement. Okay. So, since they are not statistically independent, since random variables Zi and Zj are not statistically independent, we can compute the correlation between these two random variables, call it some rho, okay, for all I not being equal to j, right. Now, we have correlation to be equal to covariance by the product of individual variances, right. So, this is the standard formula, which implies that the covariance between these two random variables is rho times sigma square, correct. Why? Because sigma is equal to sigma j, because we have assumed all of them have the same variances, therefore, the covariance is given by this product. Okay. Now, what we should do is we will have to predict the variance of the, or rather we will have to estimate the variance of the ensemble. We will have to see what the variance of ensemble is. So, now to calculate the variance of ensemble, we have Z bar to be 1 by B, right. The ensemble predicts the average of all the individual classifiers. This is the definition of ensemble, right. So, do you see that whatever we have been writing as h of x is what I am representing as z. The output of the predictor is the random variable z here. Okay. So, this is the ensemble. So, what we want to do is that we will have to calculate the variance of this. What is this? This is variance of 1 over b sum of these random variables, and note that the individual random variables are not statistically independent, right. So, what is this equal to? 1 over b squared, the variance of could have skipped the algebra. Now, the variance of sum of b random variables, what is this equal to? When the random variables are not statistically independent, we have the individual variances plus the covariance. For all the cases where I is not equal to j, we have this. We just have calculated what the covariance is, correct. Can I skip the algebra and simply write the final expression? Please do the algebra. So, finally, this will be rho sigma square plus 1 minus rho divided by b times sigma square. Please complete the algebra. Okay, we have everything that we need, just complete the algebra. Okay, now this is what is important. So, variance of the classifier, oh actually hold on, so this implies, because there is that 1 by b term there, right. Variance of the aggregate is given by this particular formula. Okay. Now, remember what was our initial goal. So, our initial goal for ensembling was that we wanted to reduce the variance of the hypothesis, the variance that appears in the Bayes variance term, so that the overall risk will reduce, correct. Now, this is what the variance was. Now, if we want to reduce this, what do we have to do? We will have to increase B. If we increase B, then the variance of ensemble decreases. So, this is the proof that ensembles always reduce the variance of a classifier, right, because the variance of the ensemble has an inverse term in the number of hypotheses that are used. The more they are, the lesser the variance is. You see that? Okay. So, this is one thing. So, one is increase the number of hypothesis functions that we are looking at, of course we can do that. There is another term here, right, which is rho times sigma squared. So, what do we do about it? So, what is this rho here? Correlations between the individual hypothesis. Now, if we increase B, okay, then this will also increase. So, if we have to reduce the overall variance, what we need to do is of course increase B by increasing the number of hypotheses, and also try to reduce this variance between, rather the correlation between the individual classifiers. Now, how do we ensure that we reduce the correlation between individual classifiers is the question. Okay. So, let us write that to reduce variance of Z bar, 1 increase B and 2 reduce rho. How do we do this? Ensure that individual hypotheses are uncorrelated. Again, there are multiple ways to do it. So, one of the ways which is incorporated in this class of algorithm called random forest is as follows. Now, random forest is a backed tree algorithm where individual hypotheses are decision trees. Now, when you are taking, remember what we studied in the last class, right? When how do we split a decision tree? At every node we consider all data dimensions and look at all possible values and compute whatever the metric is in terms of Gini impurity or anything, and then split. Now, how do we ensure that when we are building these sorts of trees, the individual trees, the predictions of individual trees are uncorrelated? One way to do this is that when you are deciding what dimensions of the data are to be chosen as candidates for deciding the split, okay, you do a random sampling at every node. Do you understand? And this random sampling is over the indices of data dimensions. Suppose there are 100 data dimensions, okay. So, you build tree 1 for the ensemble. When you are building tree 1 at node 1, okay, you do a uniform sampling between 1 and 100, you take 20 dimensions, okay, and you take only those 20 dimensions while you are deciding the first node of the first decision tree, okay. Then you come to the second node, you do another random sampling over those 100 dimensions and you take 20 of them and you build the first tree like this. then go to the second tree and do the same thing, and you build B of those trees and then construct an ensemble. This is random forest. Do you understand? Why do we do this? By doing this, we hope that since every node of the tree, the individual trees are sampled in a random manner, the correlated nature between these two decisions are lesser. So, you hope that the row here will be reduced if you do this. Did you get the random forest algorithm? So, random forest is a bagged tree ensemble, okay, where while you build the individual trees, you build it in such a way that for every individual tree, while you are deciding the split, you choose a subset, randomly chosen subset of data for consideration while you are splitting. So, you can use any of the indices, you can use the entropy index or you can use the Gini index for splitting, does not matter. Whatever index you are using, the candidate dimensions of data is randomly chosen at every node of every constituent tree in an ensemble. If you do that, this algorithm is called random forest, alright. Okay. So, hypotheses are correlated, maybe I should write it. So, one example is random forests. This is an ensemble of decision trees. A randomly sampled subset of data of data dimensions are chosen at each node of every individual tree. To reduce row correlation between them. Now, what is what could be an additional hyperparameter here? Number of dimensions that you would choose at every node. So, that is typically taken as a hyperparameter when you are building the random forest.
Sir, are the dimensions chosen with or without replacement?
Dimensions are chosen without replacement. Yeah. Any questions here before we move to the boosting algorithms? Okay, so let us move on to boosting now. In the bagging case, what did we do is that we created multiple data sets, okay, and we trained several hypotheses on each of these data sets and took an aggregate. The question is, can't we do it in a more principled way, in the sense that can't we do it in an iterative way where we search over the possible space of hypothesis, and at every time, so when we are, see, at the end of the day, what are we doing in ensembles? You take a new data set and train a classifier. Here we are training a classifier just by doing an ERM, okay. Now the question is, when we are training a new classifier, is there a principled way that we add it back to the previous classifier so that we get better performance, is the question that we are asking here. In other words, can we cast it as an iterative gradient algorithm or gradient descent algorithm or an optimization algorithm on the hypothesis space, is the question. That is what boosting does, okay. So, let me write the math. Got it, right? In bagging, we just take a data set and we train a classifier on top of it. So, now can we make it more principled by casting it as an optimization problem over the function spaces, is the question that is asked in bagging sorry, boosting. Let us define what boosting is. So, now let now here the ensemble is built iteratively as follows. Incrementally, actually iteratively in an incremental manner. Let h m of x denote the classifier or the weak learner learned at mth iteration. We get capital B number of data sets, right. So, look at each of the data set as an iteration. So, you get one data set, train a hypothesis, you get the second data set, train a hypothesis, and so on. So, you get you can look into them as m iterations. So, let HMX denote the hypothesis at the mth iteration. Now, define HM of x as hold on. So, I think I will have to use a different notation now. A capital HM of x is the ensemble that we are the next iterate ensemble that I am getting as h m minus 1 of x plus alpha m times hm of x, where hm of capital HM of x is the incremental ensemble obtained at mth iteration. See, please note this equation, right. All we are saying is that at each iteration we are building a classifier HM, okay, and scaling it with some alpha and adding them. This is nothing but the bagging strategy, right, but except for the fact that there is a scaling factor here. See, if we do alpha, if we take alpha to be 1, then it becomes simply exactly the bagging, right, where you simply add the individual hypothesis. Here you scale it with an alpha m. In fact, some algorithms, for instance add a boost, will solve an optimization problem over alpha m as well. So, what should be the weight that has to be given to each of the individual classifiers, we will come to that in a while. But do you see that this is nothing but an ensemble where we are learning a hypothesis at each iteration. Every iteration is a data set, right. You learn a hypothesis on an iteration and add it to the previous whatever we have till that particular point. Does it make sense? This is the key equation for boosting, right. So, the next we will see how to get this optimal HM and optimal alpha m, but you will have to understand this particular equation. Is this all right?
Here also we are taking B classifiers.
Same thing, yeah, you have, but you look at every data set as an iteration, you do it iteratively, right. So, you do not train each of them and then just add them. Here you take the first data set, train a hypothesis, add it to the previously existed ensemble and take next one and add it to it and so on. That this is what this equation is saying, right. For you do this for m equal to 1 to b.
So alpha can vary for.
It will vary, yes. That is why there is an index here, it is alpha m. Okay. So, what is the amount of weight that you should give for the mth classifier is something that we can control, and some algorithms actually learn it explicitly, yeah. Okay. Now, the question in boosting, so given given h m minus 1 x how to train HM of x so that the loss is reduced. We have an ensemble till m minus first step. How do we now train the mth classifier so that the mistakes that are done by m minus 1 have been corrected? So, that is the question that we will be asking. So, we will see a principled way of doing it, which is called the gradient boosting mechanism. We will stop here and continue in the next lecture.